I would like to welcome you to my presentation on non-destructive damage detection on welded threaded bolts based on electromechanical impedance spectra. My name is Sahm and I work as a research assistant in the chair for steel construction and steel composite construction of Professor Pak at the University of Sahm. One of our topics is the non-destructive testing of structures using electromechanical impedance spectra, and I would like to briefly introduce one part of our work to you today. For reasons of space, I will switch off my camera so as not to cover up the diagrams, as I hope that my diagrams looks better than I am. Here you can see an overview of the content of my presentation. First of all, I would like to show you the measuring principle of electromechanical impedance spectra so that you know roughly how the principle works. Then I come to the main part of my presentation, where I present the results of the preliminary tests as well as the cyclic tests. Finally, I will summarize the results of our investigations and give a brief conclusion. But how does the measuring principle of electromechanical impedance spectra actually work? First of all, it can be said that we are dealing here with the coupling of electrotechnical and mechanical parameters. We can measure these electrotechnical parameters with the help of piezo elements. It is the case that the electrotechnical parameters include the mechanical parameters of the coupled structure. This allows us to make conclusion about the state of the structure. This is a vibration-based method, and the excitation of the structure is done with piezoelectric elements. The structure excitation takes place in a high frequency range and in a defined frequency range. The evaluation is then carried out with the help of complex electrotechnical parameters such as impedance, admittance, or the susceptance. The first thing I would like to show you is the results of our reference measurement. For the reference measurement, 3 measurements were carried out one after the other. The results can be seen in the diagram. The conductance spectra over the frequency range from 125 to 150 kHz are shown here. It can be seen that the spectra hardly change if the condition remain the same. The correlation, which served as a damage indicator in all tests, also remains almost at 1. This shows the reproducibility of the measurements and helps to better interpret the results from the other preliminary tests. Next, I would like to show you the results of the preload test. For the preload test, a hexagon nut was clamped via a spherical leveling washer against the load cell, which was fixed between the base plate and the nut to apply a bolt preload force. You can see it right here. In the diagram, you can see the conductance spectrum for the preload stage 10 kN, 30 kN, and 60 kN. The evaluation of the measured conductance spectra showed that different stages of preload result in a significant change of the electromechanical impedance spectra in the range between 135 and 155 kHz. The increasing amplitudes correlate with increasing preload. Furthermore, a slightly shift of the resonance into higher frequency range can be observed with increasing preload. This could be due to the fact that the eigenmodes shift into higher frequency range with increasing preload. In order to detect the loss of preload, the spectrum with the full preload force was chosen as reference and served as baseline. It can be seen that an increasing loss of preload results in a reduction of the correlation coefficient. If the pretensioning force is reduced from 60 kN to 30 kN, the correlation is only 69%. If the pretensioning force is reduced to 10 kN, this results in a correlation of 58%. The measurements results are plausible and show that the detection of loss of pretension with help of electromechanical impedance spectra is basically possible. For the preliminary tests cut at bolt place, the test specimen was cut at the weld bed with a metal saw. You can see the cut right here. The depth of the cut was increased in steps of 1 mm after each measuring cycle. In the diagram you can see the graphs of the measurement series undamaged, 8 mm, 50 mm and 23 mm. A 23 mm cut depth was only quite possible because the weld seam, the diameter was approximately 23.5 mm. In contrast to the behavior of the system under increasing preload, a slightly shift of the resonance to low frequency range can be observed with increasing cut depth. You can see it right here. Between damaged 8 mm and 50 mm series of measurements, a change in the structure can be determined with the help of correlation only, as no clear trend is discernible with visual observation of the spectra. Only in the 23 mm series of measurements, a larger local peak and the visible shift to the lower frequency range is discernible. In summary, it can be deduced from the preliminary test that an increasing change in the stiffness of the structure, in this case in the form of the cut, also results in a reduction of correlation, and it's therefore detectable in principle. In addition of the preload and cut at the bolt place tests, we checked what influence temperature has on EME. Temperature is an omnipresent parameter, and its influence on EME should be compensated, if necessary, to ensure reproducible results. The diagram shows the development of the susceptance spectrum with progressively increasing temperature of the specimen. It can be seen that the amplitudes of the spectrum do not seem to change. Rather, it can be observed that the temperature increase causes a shift of spectra into higher susceptance range with simultaneous slight rotation. The rotation of the spectra can be recognized by the fact that the vertical distance between the spectra also increase with increasing frequency. This is a plausible development since an increasing temperature results in a reduction of the steel's Young's modulus and thus the modes shift to lower frequency range. The development of the spectra due to temperature is an undesired disturbance and must be calculated and taken into account for each dataset. Further investigations are necessary to provide methods for temperature compensation. The tests described below were therefore carried out at a constant ambient temperature. Finally, I would like to present the results from the cyclical tests. In order to generate a fatigue crack in the area of the specimen's weld seam, the threaded bolts of the specimen were subjected to a cyclic axial load. For each specimen, in addition to the piezoelectric elements P1 and P2, which were already used in the preliminary test, 4 strain gauges were applied to the stud shank above the weld in order to record the surface strain in axial direction. You can see the strain gauges right here. The arrangement made it possible to measure the strain change over the circumference of the shank during the tests in order to sense the introduction of the fatigue crack at an early stage. In case of specimen 1, a fracture occurred near the weld zone after 171,000 load cycles. In the picture you can see a light gray fatigue area and a dark gray brittle area. Both are typical characteristics of a mixed fracture. In the picture you can see that the fatigue crack starts in the area between the strain gauge 1 and the strain gauge 3, here, and grows towards strain gauge 2 and strain gauge 4, right here. The EME measurements were evaluated by analyzing the conductance spectra. The conductance spectra showed that the amplitudes increase with increasing number of load cycles and thus increasing damage. You can also see a shift of the resonance to lower frequency ranges. In the last test series with 170,000 load cycles, it can be seen that a second amplitude appears at about 133 kHz. Here you can see the first amplitude and here you can see the second amplitude. The diagram clearly shows that the correlation decreases with increasing number of load changes. Furthermore, the development of the axial strain over the circumference of the bolt shaft was evaluated. The picture shows the qualitative development of the axial strain measured with strain gauge 1, as well as the correlation of the susceptance and conductance spectra after the respectively load cycles. Plotting of the related strain has the advance that the qualitative strains developed can be compared with the data of the EME measurement. Between 0 load cycles and 132,000 load cycles, the graphs of the three monitoring methods show a very similar trend with a slightly decreased slope. After 130,000 load cycles, the strain and the correlation of the spectra are at about 93.5% of the original level. After a further 16,500 load cycles, the strain dropped by 22%, while the correlation coefficient of the conductance and the susceptance spectra has a value of 91%. From 149,000 load cycles, the correlation of the susceptance and conductance spectra also drops significantly. After 164,000 load cycles, the correlation is only 66% and 69% respectively. Finally, I would like to give a little summary of the results. The preliminary tests and subsequent cyclic tests have shown that it's possible to evaluate the condition of a steel bolt with the help of EME. The preload tests have shown that the resonance tend to move into higher frequency range as preload increase. We also could see that the eigenmodes also shift into higher frequency range. The results from the temperature tests are that the linear diagonal shift of the resonance into lower frequency range and a slight counterclockwise rotation of the spectra. From the cyclic test we can see that it's quite possible to detect fatigue cracks at the base of the well-threaded bolts. That brings me to the end of my presentation. Thank you for your interest and stay healthy.